version of this talk, but hopefully there will be something new for everyone. So today I'm talking about this price formation mean field game model. And this is a joint work partially with a former student of mine, João Saúde, and part of it with my current student and former student, Julia Gutierrez and Ricardo Ribeiro. So what we are interested is in the following. We have, and this was, let's say, our original motivation is that we have a large number of agents, and each agent owns a storage device, maybe a battery, that can be charged and later supply the grid with electricity. And they want to trade this electricity, and they trade at the price for pi, and this price is set in such a way that supply balances demand, and the supply is given. Now, although the original motivation of this model was electricity markets, in fact, this can apply for any commodity that can be traded and stored. That can be extended to multiple commodities without any serious changes, and we can change the model. So this is somehow the simplest model we can come up with, but you can have decay, spoilage, storage costs, limits, and so on. So there are a number of natural generalizations. We are working with some, and there are many others that can be considered. So let's start with the deterministic framework because it's somehow easier to understand. So our model has three quantities of interest that we want to determine. So we want to determine a price, we want to determine a value function, and we want to determine the distribution of agents along time. So these three things are unknown given the supply, and the way these things are determined, as I'll explain later, is by solving a system which comprises a Hamilton-Jacobi equation together with a transport or Fokker-Planck equation, together with an equilibrium condition, together with initial and terminal boundary conditions. And it will be clear why we care about this kind of problems and why it is set up in this way, but I just want to give you, so you are given a deterministic supply, you want to find U, you want to find the M, you want to find the price, and that in such a way that there is a terminal value and there is an initial distribution of agents, and these are the things that you want to determine. Oh, wait, I need to erase this. Okay, so U is the viscosity solution of the first equation of the Hamilton-Jacobi equation. So the first equation here, and is the value function for an agent whose charge is x at time t. M is a solution to the second equation, and it gives the distribution of the agents energy reserves at time t, and the spot price is such that the supply balances demands, and this is the condition imposed by the last equation. Now, so the way this is set up in the deterministic case is that we, in fact, our main result in the deterministic case, and this is joint with João Saúde, is that in fact we can find a solution, we can find a U, we can find a probability measure M, or a pattern probability measures M, and we can find a Lipschitz continuous price. Okay, so another interesting case that I'll address later on is the stochastic case. So instead of having a supply that's deterministic, we have a supply that evolves by a given diffusion, and this diffusion depends on the supply itself, depends on the price, which is an unknown. And what we want to find again is a solution that the price that's given in somehow feedback form and ensures a market clearing condition, ensures that supply meets demand. So these two problems are somewhat in the same framework, and the question is, can we solve them, and can we get them? I mean, for the stochastic case, actually, this may not be always solvable, but at least in the linear quadratic, we can do this thing. And the key technique is to use some extended state space. So without further ado, I'll start by looking at the deterministic model and explain where these terms come from, and then hopefully everything will be clear when we get to the stochastic setting. So consumers have a storage device, a battery, which is connected to the network. They trade electricity, and what you want to do, of course, is to buy low and sell high, and they take into account battery price and battery wear. So what happens is that you have a charge. So the agents have a charge. They control the charge by choosing a parameter alpha, rate alpha. And what they do, the way they select this in this deterministic setting, is that they minimize their cost. And their cost has two parts. One, which is, let's say, a running cost that takes into account the trading costs, the storage costs, and so on. And you have a terminal cost, which is something that encodes your terminal preferences. So at the end of the time horizon, capital T, you'll have a certain stock, X of T, or a certain storage or charge, and you value it in some way. So for the terminal cost, there are many natural choices. For example, maybe you don't have a preference, and then you would set up U to be identically 0. Maybe you have a preferred state, and then you choose your terminal cost to be something that has a minimum at your preferred state and it's convex. Or in some finance problems, there is this thing called the liquidation problem, which is this, well, you want to end up with 0. I mean, usually for charge, it doesn't make sense to end up with battery fully discharged, but if you are selling stocks or something like that, then you may want to end up precisely at 0. So you want to set your cost to be plus infinity, except if you are at the minimum. Now, so this is somehow 3 examples of how this terminal costs can encode various preferences for your terminal state. And now the question is the Lagrangian. Well, so recall that what the agents are trying to do is to minimize a running cost plus a terminal cost. So I discussed the terminal cost. Now I'm going to discuss the running cost. And so the running cost has 2 parts, and one which is somehow forced upon you by what the price means. So if you trade at the rate alpha, you pay price times alpha, right? This is what price means. It's really, and then you have other things that may be costs that you incur. For example, maybe if you're talking about the battery, you have battery wear and tear. So if you choose a very large current, you pay a price. Maybe you have some decay or some costs in storage, and these are encoded in this potential. And if you put these things together, then you have as your cost in this example would be the price times the trading rate, maybe something that encodes wear and tear, maybe something that encodes wear and tear based on the charge. For example, this running cost can be seen as a temporary price impact. If you go back to this formula and you look at this term together with this term, what you see is that in fact what you can think that the term like this means is that in fact if you trade at the rate alpha, you are paying C alpha over 2 more. So if you are trading at a high trading rate, you pay the market price plus something the market impact, and this is something observed in for example stock markets. So if you give very large orders, you impact the market and you pay more than the spot price before you have given the order. so you pay an effective price, and this is one way to look at this running cost as some price impact. Another thing is that maybe you have hard constraints. For example, if you have a battery, you certainly cannot exceed the maximal charge, and you cannot go into negative charges. And this is exactly what happens in this situation here, when you put a potential, which is plus infinity if x is less than 0 or x is greater than 1, right? So, so there are a number of ways to describe things like this. And in fact, if you look at the oil prices in the last few days, actually, you had problems with things like this, because in fact, the collapse in oil prices somehow reflect, sorry, not this part, but this part, that the storage limits have been achieved, and somehow people cannot buy anymore. So now, so this is the problem. You have an optimization. You have an optimization problem, and this gives rise to the value function, which is the least possible cost you can achieve. So among all trading rates, you try to minimize all your choices, given that you know the future. Again, we are looking at the deterministic case, so you know the supply for all times, and you know everything for all times, and you know the price for all times. And now what's standard in let's say optimal control theory is that this value function, is a viscosity solution of a Hamilton-Jacobi equation. And this Hamilton-Jacobi equation gives you the following information, that in fact, your optimal strategy is always given in feedback form, at least in points of differentiability of U. Meaning that if you give me a solution to the Hamilton-Jacobi equation, you can use this solution to build an optimal control, an optimal feedback control. But of course, this assumes that you know the price. And the question is, how do we determine this price? Because part of the problem is find the U, find the price, and find the distribution of agents. Now, this is what I need to address next. So just to give you an example, because this will be a running example, if you take L0 as before, which is just V squared over 2 minus a potential, then the Hamiltonian, actually, this should be a minus, it's a plus. The Hamiltonian associated with this Lagrangian is this one, and you get the corresponding Hamilton-Jacobi equation. And this is the controls in feedback form. Okay. Now, associated to this, what you have is a transport equation, because the agents are going to use the optimal feedback, which is this one, and they are being transported. So the idea is that you have multiple agents. Let's see, you have multiple agents. And this is one-dimensional, but each agent is following the optimal feedback, the optimal strategy, and the initial distribution of agents is moved somewhere, somewhere in time, and this is given by solving the transport equation. So in the running example, this is the transport equation that we are talking about. So it's a first order equation. By the way, if you have questions, you can ask, or unmute yourself and ask, or just send me a message and I'll see it. So once we have these two ingredients, so if you give me, we have an equation for U, we have an equation for M, and now we need an equation for the price. And this is where the mean field game model enters, because this is where we require that the demand, which is the amount that you trade, matches the supply. And this is given. This is given. And of course, we require that demand matches supplies, where demand is given by the optimal strategy of the agent. So these are rational agents. They use their best strategy, and somehow this constraint determines the price. So we have these three equations, and what makes it hard is that they are coupled. So if you look at this example, I mean, we know a lot about Hamilton-Jacobi equations. We know a lot about transport equations. This is just an integral constraint, and you see, if you look at this integral constraint, you can actually write it as this thing equals Q. So if you give me U, you give me M, you can solve for price. But these three things together, because you don't know U, you don't know M, and U and M depend on the price, and they are coupled with terminal conditions for U, because you see the agents have a terminal target that they want to reach, and they are coupled with initial conditions for M, because the only thing that you know is where the agents are in the beginning. So these equations are fully coupled. So it's not completely obvious that first you have a solution, and whether you can actually work out the examples and get these solutions in practice. So this is somehow the critical thing here. Now, if you have seen optimal transport, you'll see that actually this model is very similar to the Benhamou-Prenier optimal transport problem, formulation of optimal transport. And I put here the price model in red. So black and red are the price model, and black and blue are the Benhamou-Prenier optimal transport formulation. So we can see as this price model as somehow a constrained optimal transport, maybe with some different boundary conditions. The optimal transport, you are given two probability measures, and you want to transport M0 into M1 optimally. Whereas here you are given an initial distribution at terminal costs, and you want to get these things. And in fact, if you look at this, you'll see that the price model is actually the optimality condition for an optimization problem, which is a linear optimization problem in space of measures with similar constraints to the Benhamou-Prenier formulation, but with an average velocity constraint. And then the price, if you look at the formal optimality conditions, what you realize is that the price is somehow the Lagrange multiplier for this constraint. Sorry. Okay. Let me just erase this. So what I'll discuss here, this guy was deterministic, but actually we can make it also depend on the price. There is really no problem as long as this map is non-decreasing, meaning that if you increase price, you increase supply. And if you don't, then the problem becomes much more challenging, and probably all kind of weird behaviors will happen. So before we go through the general theory, which I'll address in the end if I have time, I want you to go through a bunch of examples, because I don't think everyone is familiar with min-field games, and an important example is finitely many agents. And let me describe the solution. I'm not going to prove anything, but I'll describe the solution. So the idea is that you have an agents. The way to think of this is that you have the X, the supplies, and maybe the agents have a certain charge, and they want to optimize their trading costs. And so these agents will continue to be agents. So later on in time, maybe the agents will be somewhere else, but they will be still direct delta. So you're looking for solutions like empirical measures. And if you do this under natural convexity conditions, then we can find a solution by a quite interesting means, which is this: you build the Hamiltonian system with a constraint, So you need to solve the Hamilton's equations, but there is this extra variable, which is the price. And the price is the thing that gives you the constraint with boundary conditions that are the initial conditions and the gradients of the terminal costs. This problem turns out to have a unique solution under these natural convexity conditions. And what you can do with it is that you can assemble a solution. So if you have a solution to the price model with initial terminal conditions, which are empirical measure and cost, then the piece from before are the gradients of use. This is somehow the method of characteristics. And M is just the empirical measure along the trajectories. So for finitely many agents, the point is that you can look at these mean field games and simply convert them into finite dimensional Hamiltonian systems with an additional, somewhat non-standard constraint. But this is something that has been studied quite a lot in the literature. Hamiltonian systems with constraints are reasonably well understood, and this is exactly one of them. So this is how finitely many agents can be put in this mean field game framework. And in fact, there is a nice variational principle, which is this: the agents are actually minimizing the costs. I mean, this should be L0. Well, it doesn't matter, but they are minimizing their trading costs with a constraint that supply meets demand. So this, if you look at this, and in fact you can put L0 or you can put L, doesn't really matter. So you can imagine that the agents are minimizing the market impact without any regard to the price, and this is nice variational formulation for this. And then you can show the existence directly, because this is just a finite dimensional direct method of calculus of variations. You can also put constraints, for example, and this is actually something interesting that can be also addressed. Now, let me explain a little bit the stochastic model. So this is the next topic to explain. So in this case, the situation is a bit different, because we have a supply and a price that is progressively measurable. So the price is random. So for every realization, maybe the price is random and the supply are random processes. So we have a quantity, a commodity out by the agent. The agents control their trading rate, and they want to minimize a similar function as before. So they want to minimize a similar running cost plus price plus terminal cost. Except that now I need to tell you how this thing is going to solve. And the idea is this. The idea is that you are given a supply drift and a supply volatility. So what we have is that the supply solves a stochastic differential equation, dWt. And what you want to find is this. You want to find U, you want to find a price and volatility and coefficient such that you have a solution of this system here. And this system is comprised by a Hamilton-Jacobi equation, a stochastic transport equation, and a balance condition. And the difference here, and for this formulation to work, is that you need to find a solution in this extended space. So U is a function of your state, the price, sorry, the supply, the price, and time. So the first equation is an extended control problem. So this is a control problem where the agents will control their supplies, but they also see the price, and they also see, sorry, they also see the supply, and they also see the price, which also solve coupled equations, coupled stochastic differential equations. So, and if you look at this map, this is a stochastic map. So you start, let's say, in the XQ price space. You start, you go somewhere, you end somewhere, and now you can imagine that you have multiple agents, and these guys are being transported somewhere. So this stochastic differential equation induces a random flow. Of course, for another realization of the noise, maybe you'll end up somewhere else, and these guys will end up somewhere. So what we have associated to this stochastic equation is not a deterministic flow like the transport equation, but a random flow. Okay. And this is why we need to look at this stochastic transport equation. So the stochastic transport equation, the big difference is that there is an additional term which has a Brownian motion. So this is stochastic PDE, not partial differential equation. And of course, you may be wondering, what does it mean to be a solution of this stochastic PDE? And the definition is just being a solution in the weak form, meaning that you have an identity that is what gets by multiplying the function, the equation by a test function and integrating by parts. And you see that now this is a perfectly well-defined identity, let's say integral identity, where the last term is a Nito integral. So it's a stochastic integral, not the standard integral. But there is nothing nothing particular mysterious about the meaning, as long as you understand these equations as in the weak form. Now, what is this? Yeah. Okay. So now let me. So now that we have these two models, let's go through a couple of examples, and I'll start again with the deterministic, and then I'll address the stochastic case later on. Mostly in examples, I'll tell you a little bit about the theory. So let's go back to our deterministic model. Quadratic Lagrangian. This is the coupled Hamilton-Jacobi equation, so the transport equation, and let's call it the balance condition. So these equations are the three equations that we need to solve. And what I would like you to convince is that as long as you are in the quadratic world, that these things have solutions. So these things can be solved, and you can get, let's say, formulas out of it, and at least as a sanity check. Of course, we can also prove the existence under general conditions, but we would like to get also a couple of examples, and these examples is what I want to focus right now, especially to give you some intuition of what's going on. So what do the agents do? Well, what an agent wants to do is to minimize a running cost. So this is your trading costs, and this is your, let's say, market impact costs. And if you look at this, this is a one-dimensional variational problem. So there is a corresponding Euler-Lagrange equation. Now, if you look at this Euler-Lagrange equation, this is a derivative. So you can integrate it, and you get this thing that I pompously called the optimal consumption rule. But it's just a reflection that if the price is high, you buy less. So this corresponds to our intuition, and it's good that the model is giving something that corresponds to our intuition. Then it's okay. So we have this trajectories. Of course, we don't know theta, right? So each agent needs to determine its own its own theta. But now we look at this and we'll say, well, let's try to figure out something. Let's look at the Hamilton-Jacobi equation. Let's differentiate it and multiply by m and integrate by parts. And what we get is a very remarkable identity that the time derivative of uxm is 0. So in fact, when you write down the balance condition, what you get is that the supply is some capital theta minus the price. So we have a linear price supply relation, meaning, again, same principle, that if the supply is high, the price is low. So supply high, price is low, and the other way. And if you've been following the news, you will not ask the question that generally people ask me at this point, is can the price be negative? And if you've been following the prices of the oil, you realize that yes, price can be negative and you can actually get paid to get stuff, provided, I guess, you have storage space. So if you have a few barrels at home, maybe you can make some money out of it. So now let me go briefly about these computations, because I just want to convince people that this is something that can be solved. So you look at the single agent and you can integrate the trajectory of a single agent just by integrating the derivative, and you get the formula, right? And if you look, because we know x dot, right? Because we know x dot, we can get an optimization problem for a single agent, and this is just x dot. This is just x dot. This is just the price, and this is just x of t. Okay. And this formula looks quite involved, except that this is a finite dimensional, because theta is just a real number. So we can solve if you give me capital theta, if you give me this number, because again, this is something that we don't know yet, then we can solve for u. And in fact, this is the idea. For each capital theta, we determine a u capital theta, which is just the solution of a finite dimensional minimization problem. I mean, it's one dimensional minimization problem. So this is a real parameter. This guy is a real parameter. We have this finite dimensional minimization problem, and now we say, well, but we don't know this theta. How do we get it? Well, but we go back to its definition, and what you see is this. Well, you just get the optimality condition. So given theta, we solve the Hamilton-Jacobi equation for the theta. We use the resulting expression in the definition of theta, and now this is a fixed point. So this is an equation that can be solved. Well, provided you get formulas for these guys, because this is known. And this you just computed. And in fact, if we go through the algebra, and I'll spare you the details. If you have, for example, a quadratic cost, what you get is, well, a special formula for your theta, which doesn't look that good. But again, just to convince you that one can get these formulas fairly explicitly in this quadratic world. And out of this, we get an equation. This is the balance equation, which gives me theta as a function of theta, and then you can solve it, and you get some formula. Okay, so we get precisely a formula for the price. K0 is the total supply, integral from 0 to t to q. X bar is just the average, and this is your target. So this is basically the what we get. So in this case, we actually use this to compare with some let's say previous results. Oh, let me just give you this. So one thing that we get is that each agent solves the dynamics, which has a mean reversion term. So we want to get as close, and driven by supply. But of course, we need to know X bar. But if you go through a little bit of computations, what you realize is that X bar is driven by Q, as it should be, because, well, that's what the supply is doing. So in the end, each individual agent can determine its trajectory by solving a system of two ODEs. And this is a closed system of ODEs that only involves Q and the parameters of the problem. So this is something that can be solvable pretty explicitly. And in fact, what we looked is what would happen if we were using this to smooth out the consumption in this case in the UK. And we compare this model with the model by De Paula and his co-authors, where the idea is that they create an energy price, which is a function of, so in their case, of the aggregate consumption. So in principle, it can have an imbalance. And the idea is that probably some coal burning central would make up for the difference. But here, what we did, we calibrated our model against their models and tried to see what kind of prices do we get. In particular, we are interested in knowing whether we get smoother prices, so smaller peaks, and this is in fact the case. So if we look at the price for our model at the peak hour, this is exactly what happens there. It's exactly what happens here. So we have the orange peak, which is our model, is much more smooth than the other one. Okay. Now, let me go briefly about the linear quadratic model, stochastic case. So the stochastic case, you cannot solve it in general. So this is the thing, but you can solve it in the linear quadratic case. And the idea is this. Well, if you have, let's say, this is what you are given. This is what you are given. And this is unknown. But suppose for a moment that they are linear. Okay, someone tells you, oh, look, you don't know what BP is and what sigma P is, but we know that they are linear in QW, and also that H is quadratic. Well, in this case, what you end up is with a Hamilton-Jacobi equation, which is linear quadratic, and these things are known to have linear quadratic solutions by solving Riccati equations. Now, so these equations are solvable in the class of second-degree polynomials. If you do that, then you can write what the balance condition is. And a nice thing about second-degree polynomials is that, well, their second derivative is just a constant. This is just a function of time. So the balance condition, which is the really hard thing to do because you have an average of this derivative with respect to this probability measure. In this case, you can pull these coefficients out of this average. And this is exactly you get formulas for the price and for the diffusion coefficients. And this problem becomes solvable. This is somehow the key idea here. And let's just give you an example and show you what results are. I won't go through all the computations, but So let's say you take a quadratic Lagrangian, you take target alpha, you start with a standard normal distribution, and you start with a supply that's mean reverting, okay, with let's say starts at 1. And we want to see, as a function of alpha, how does the price depend? How does price depend on alpha? And well, we'll just run some simulations. We get the formula because we solved the previous coefficient, so we get the formula for the price, where the coefficients A are given by in terms of Riccati-like equations. I mean, they are kind of nasty equations, but they are just solvable, or at least numerically solvable. And this is precisely what we are getting, that when alpha is 0, so when agents don't want to end up with any stock, then the prices are lower. As you increase the target, the prices go up. So the prices are these colored things, and the supply is in gray in the graph. So you see that, as you expect, as more and more people want to get more, you get higher prices. Okay, now I still have 15 minutes. So this is so there are a number of other things that we can do. I mean, we can do more general linear quadratic. One thing that we are doing in this random case is to looking at finitely many agents, so with random supply but without individual noise. And this is something that just uses calculus of variations. I mean, the general case is still open, I think, but we'll get there, I hope. Let me just go back to the deterministic problem and explain how we can address the general case. Because so far what I did was, well, I came up with a model, with a price model. I showed you how to solve quadratic cases for the deterministic, quadratic cases for the stochastic, but of course you would like to get a general theory. If your Hamiltonian is not quadratic or your terminal costs are not quadratic, can we solve it? Do we have solutions and so on? So let me remind you the problem. So we are given an energy supply rate. We want to solve a Hamilton-Jacobi coupled with transport or Fokker-Planck coupled with the balance condition with initial terminal data. So this is somehow the problem that we want to solve. And because every equation depends on the others, you cannot just use standard theory to say, well, such a system has a solution immediately. In fact, you need to work a little bit. And the way we do this is by a fixed point argument. So what you do is this: suppose this price is given. So given price, you can find u. Given u and price, you can find m. And well, given u, price, given u and m, you can find a new price out of the third equation. Now, if you do this in this way, this actually doesn't work so well, because what you want to show is that the map, this is now a fixed point problem, and what you want to show is that the map that takes price into price by this process is compact, so that you can apply a fixed point theorem. And this is where we need a little bit work to get this compactness. So let me show you how this thing goes. So there are a number of technical assumptions, but essentially it's uniform convexity of the Hamiltonian. This is the thing that plays a critical role. I mean, we have some technical assumptions on third derivatives and some bounds, because you always need some kind of bounds in this business. So under these assumptions, what we are going to do is this: we want to prove bounds for u uniformly in price. Okay, And you want to cascade these things until you start with a price that maybe it's completely crazy, and after this process you end up with a price that it's in a better regularity class. And then what you want to do is a fixed point argument for this thing. So let's see. So about the Hamilton-Jacobi equations. So one thing that's quite interesting. I mean, I don't think it will surprise the experts in Hamilton-Jacobi equations, but certainly if you have never seen it, it's kind of surprising. Is this: no matter how irregular this guy is in time, let's say it's a continuous function, but completely insane, then you have local bounds, and you have Lipschitz bounds on U that do not depend on price, and you have semi-concavity bounds which don't depend on price also. So this is something that's universal. So if the price is bounded, let's say you have bound for U, and uniformly in the price, you have Lipschitz bounds on U and semi-concavity bounds which are uniformly in the price also. And this is a very nice trick in control theory for Lipschitz semi-concavity, for example. The idea is that you take a minimizing, so U is a solution of a control problem. You take a minimizer, you shift the minimizer to the right or to the left, and what happens is that the price cancels in the inequality. So the standard proof of semi-concavity doesn't see the price, and because this thing cancels in the proof. So that's why you get the semi-concavity estimates, which are uniform in the price. Now, once you have this, you have stability. So if you have uniform convergence for the price, then you have local uniform convergence, and almost everywhere convergence for the gradients. So this is one thing. Then you go to the Fokker-Planck equation, and you have continuity with respect to the Wasserstein distance, the one Wasserstein distance. And here we need to solve the case where epsilon is positive, and then there is a delicate limiting procedure to send epsilon to 0 and in the general case. So the existence is fairly standard, and this continuity is fairly standard. And we have continuity, for example, in L2. So if you have convergence of the prices, then you have convergence of the U's, you have convergence of the derivatives, and you have convergence of weak solutions. So once you have that, then there is a critical bound, and you'll see why this is important for second derivative of U, which is one of the tricks of the trading mean field games that has to do with some differentiation and integration by parts. But once you have this, then you are in good shape to the next step. The next step is somehow the critical step here. And this is this idea. Okay, so let's start to try to explain what's going on. If you have a Hamiltonian, let's say p squared over 2, dph is just p, right? So this quantity here is price plus ux, when this is computed at x0. So. And you say, well, if you give me u, you just integrate this guy, so you can solve for price automatically. The problem is this, and of course you can do this for one time, for example, t equals 0. But the problem is that this quantity in general could be fairly irregular in time. And because of this, if you just solve this thing, at time t, for every t, you may end up with the price. So you start with the price, you get the u, you get the m, and then you try to get a new price, right? But the problem is that this new price can be quite irregular, because it sees UXM, this thing. And this quantity here can be quite irregular in time. So we need a better way, because otherwise you don't get compactness. So this is the key thing, is that at one point you can solve, but if you solve this for every time, then you have an issue. So the way this is solved is a bit different. What we do is that we find an equation for the price. We look at the balance condition and we differentiate, and we get an identity. And you say, well, this looks kind of bad, because where you had an equation that's strictly monotone in the price, now you have a differential equation with some nasty coefficients. But the point is that this quantity here is bounded by below, because that's one of the strict convexity assumption. And this quantity here, as we'll see, is bounded. Okay. And this is exactly the thing that we get. So if you look at the quantity that's inside this parenthesis, we can use the equations. Sorry, the quantity that's in here. We can use the partial differential equation for u and m, and we can simplify it. And this is where we need this third derivative. If you remember, the third derivative rises here as part of this regularization procedure. And what we get is an equation for the price where everything on the right-hand side is bounded. So in fact, what you have is, you have this price tracking ODE, which is quite messy, but shows that the map takes price, U, M, price, and this guy belongs to W11. Okay, it's not really Lipschitz, it's W11, but that's enough to get compactness. Okay, and this is basically, sorry, this. And of course we need to check continuity and so on, but somehow the key property is that the right hand side of this equation, this guy here, is in L1. Okay. And because the denominator is always bounded, the denominator is always bounded, everything else is part of the estimates that we have. So once we have this, then we have stability of this equation. This is actually W11, not W1 infinity. And we get the stability and we get the compactness for this map. And once we have this, then it's easy to see that there is a fixed point by Schauder's theorem. So this map is compact. I'm sorry, this W1 infinity is working from some previous version, but so by Schauder fixed point we have a price, and once you have a price, then you have everything. Now this is for epsilon greater than 0. For epsilon equals 0, the real difficulty is passing to the limit, and for this we use the vanishing viscosity method. The real difficulty is to show that M solves the transport equation, because we are passing to the limit an expression that is nonlinear in UX epsilon M epsilon. And for this, we use some methods. We use some phase-space measures and borrow some methods from weak KM theory to get exactly this to be able to pass to the limit in objects like this, where you have a nonlinearity in this problem. So then what you can do is a little bit more. Is you can look at what I call natural convexity assumptions. And in fact, if natural convexity assumptions mean basically the following thing, that your terminal cost is convex, your potential, so U bar, your potential is convex, and so on. And if you have that, you have more regularity, and this gives you unique, it gives you a lot more regularity for the solution. So in the last 1 minute, let's say, let me just address briefly the uniqueness. And the uniqueness relies on identifying a suitable monotone operator. And this is really the identity behind the Lasry uniqueness proof, Lasry-Lyon's uniqueness proof. And the thing is that the operator that is monotone is an operator that takes mu and the price into the Hamilton-Jacobi equation, transport equation, and the balance condition. And it's just a simple computation to check that this operator is monotone in this L2 sense. So if you have two solutions, and it's strictly monotone under mild conditions. So if you have two solutions, and if M and M tilde are absolutely continuous, the monotonicity gives you that the prices are the same, then the U's are the same, and if U's are the same, then the M's are the same. And this is okay for epsilon greater than 0. For epsilon equals 0, it will be okay if you work under this natural conditions. Okay, I think that's all for today. My time is up, so thank you for your attentions. If you have questions, let me know. I'll be more than happy to answer them.